Hi everyone, I'm Huxin from National University of Singapore. The topic of this paper is a remote center of motion recommendation toward brain needle intervention using deep reinforcement learning. The contents include introduction, method, results, and discussions, conclusion, and future work. Brain disorders are diseases that are very harmful to human health. It includes injuries, brain tumors, neurodegenerative disease, mental illness. I see from the table a large number of people affected by brain disorders, typically Parkinson's and brain cancers. And some of them are required to undergo some clinical procedures for diagnosis and therapy. Among them, a typical procedure is needle intervention. A needle-based intervention is a typical kind of minimal invasive surgery. It has various applications, including biopsy, deep brain stimulation, seek, drug delivery, brush therapy. However, most are conducted manually by surgeons. It has some limitations. High reliance on surgeons' expertise and experience, human conditions during procedures, and accessibility to the patient's tissues. All of these have impact on surgical accuracy and will further cause multiple needle insertion and multiple lesions. To solve these problems, we designed an interventional robot. It has the following features. It is a skull-mounted robot, has 4 degrees of freedoms, has parallel structure with RCM mechanism, and more importantly, it is MRI compatible. If you are interested in this paper, this robot, you can refer to this paper. And for our robot, the clinical steps are shown in this diagram. Firstly, we need to choose a fixation position to mount the base on the skull and do MR scan to obtain the 3D position of the target and choose an RCM and drill the burr hole. You can also view the RCM as the burr hole. Finally, we need to mount the robot on the base. Okay, the RCM is the keyword for this paper. It is the abbreviation of a remote center of motion. Therefore, how to choose the RCM is highly associated with needle path planning. This process should satisfy several clinical and mechanical requirements. For clinical requirements, it is about safety issue. During needle insertion, the needle should avoid blood vessel, some nerves, and tissues. Precise brain shift and tissue deformation had better to be taken into account. All of these are criteria 1. It is named by COA, clinical obstacle avoidance. Additionally, based on the structure of the designed robot, there are 2 mechanical requirements as well. The first is about solvable IK inverse kinematics for the robot to guarantee robot working normally in the operation. For example, if the target is over there, the red point, if RCM is here, robot can work normally. But if here, the robot cannot work. So this is the criterion 2 named by MIK, mechanical inverse kinematics. Criterion 3 is about less motion of the robot joints because less motion can reduce the hysteresis and friction in transmission part for the real robot and reduce its motion coupling. For example, if the RCM is chosen just over the target and below the center of the robot, the robot does not need to move. So the position of the joints are all 0. But for this, if the RCM is here, the position of the all joints are bigger than the former. So this process may include mechanical errors. So this choice is worse than the former. This is a criteria 3 called MLM, mechanical less motion. So in this paper, we propose to use reinforcement learning to combine the clinical and mechanical requirements for RCM recommendation. To simulate the operation, The robotic needle intervention scene is constructed in VRAP, a robot simulation platform, because besides we use ROSE as interface and SolidWorks as modeling tool. The entire simulator contains some entities like needle, robot, and some virtual entities, and needle parts, and range of motion of RCM, something like that. And after that, we also need to establish reinforcement architecture. The RL environment consists of active components, targeted suspicious tumor, blood vessel is obstacle for criteria 1, COA. Robot it has constraints, MIK and MLM. The RCM is the agent. Therefore, the observation of the environment includes target position, robot joints, RCM position, and the action of agent. The observation is need to be normalized by using maximize normalization method to range from -1 to 1. After building environment, a reward function needs to be designed. According to 3 criteria, we have the following 3 reward component. In the first equation, D1 is the minimum distance between blood vessel and needle parts. If D1 is over than a threshold, this means this needle pass is okay, is safe. At this time, the reward R1 is 0. Otherwise, it is negative following this linear equation. For the second reward, R2, if D2 is 0, this indicates if D2 is 0, this indicates robot inverse kinematic is solvable. Otherwise, it cannot. R2 is set -1. Last reward is the average of 4 robot joints. This means this meets the criterion MLM. Then, according to the importance level of criteria, we have this relationship and define corresponding weight. MIK is mandatory. We have to guarantee a robot can work normally in the operation. And COA is second important, and MLM is just optional. Finally, sum them up to build this equation. This is the complete reward function. Finally, we set the terminal condition based on the number of interaction steps and each criteria. For the agent side, the action is executed by RCM along X and Y axis. The action range is from -0.5 to 0.5 millimeter and keep constant in Z direction. The agent algorithm is PPO. The network is constructed like this diagram. The loss function we used is the clip type. To make a benchmark for comparison with RL agent performance, we manually mimic the process to collect expert data. So a master-slave teleoperation system is established. On the master side, the haptic device is used as a manipulator control to move the pen tip on a circular plate. The haptic interface point of the device is transmitted to PC via ROSE interface, then mapped to pen tip, and finally sent to VRAP via VRAP ROSE interface. In this step, 7 RCM entry points are chosen to replace the stochastic process of randomizing RCMs. And for each RCM, 5 different randomseeds are employed to generate 20 targets. Therefore, 140 sets of data are collected. Besides, to demonstrate the impact of the optional criteria MLM. We define two reward functions, two criteria groups to make comparisons. W123 includes all criteria, while W12 just includes criteria 1 and 2. From this plot, we obtain two mean scores for the two criteria group. We also use two RL agents to perform this task and make comparisons. Yellow indicates the baseline, and blue and red show the results of the DBG and the PPO. After 60% episodes of training, both RL agents' performance converge and outperform experts' baseline. For detailed comparison, the last 40 episodes of the averages are computed and plotted in these bar graphs. PPO from this bar graph, we can find the PPO agent performs best, and it has stable learning performance. To evaluate the agent performance visually, RCM recommendation example is shown in this video. In this example, the trained agent is PPO. Initially, the virtual needle path collides with the blood vessel, and the kinematics of the robot cannot be solved. So the agents then control the RCM to gradually far away from blood vessel and try to search solvable inverse kinematics. At the same time, the agent try his best to satisfy the third criteria MLM until the terminal condition. Okay, this is the recommended RCM. So in this paper we design a reward function according to clinical and mechanical constraints, COA, MIK, MLN, and we also use reinforcement learning to finish RCM recommendation task. So next for our future work, we will use environment models with high fidelities like this, and add more constraints, tissue deformation, brain shift, shown like this, and try a steerable needle like this, because currently we just use a rigid needle. For rigid needle, some collision between blood vessel and the needle is unavoidable. So a steerable needle can solve this. So in the future, we will try to use a steerable needle. Okay, thanks for listening.